let's go for the second part of this week, say this matrix calculus instructions or guidelines or motivation or whatever you take it for. This week I will have shorter presentations in this course, but that's because the topic I will be touching in this presentation is actually much harder than whatever we did before, except of the Baron-Frobenius theory, which we didn't touch much. And so I want to leave space for those of you who would really like to struggle a bit and go through. But before diving into the ultimate decision of what to do with the eigenvalues and eigenvectors and how to see some normalized form of our mappings in coordinates, I will add some remarks on the self-adjoint matrices. And you know that if I have in real numbers, if I have A and I take A times A, so it will be A squared, and that will be always bigger than or equal to 0 in R, right? And if I do the same with matrices, then it doesn't work, right? So it's A times A, it's not very nice, because it could be quite, well, it's again A squared, but what to say about it, we don't know much. But if I take A times A star, so recall that A star means I use both operations I have at my disposal, so I can conjugate the complex matrix A and I can transpose it, right? And in case A was unitary, then this gives you the inverse. If it was self-adjoint, it gives you the same A. And such a matrix is always self-adjoint, right? Because, of course, I mean, if we just hit it with, well, maybe I will rather write something else. So if I hit this with U, so that's the, rather I will write it, yes, if I hit it with U and again U with scalar product, then of course, because we know how to write the adjoint, so this will be equal to A star of U, A star of U, and we know that this will be always real and it will be bigger than 0. So you see, this is a very special feature of the behavior of matrices, and we call these matrices to be positive semi-definite if they have this kind of behavior. They are self-adjoint and have this behavior. This is equivalent to the fact that the self-adjoint matrices, as you know, have got always real eigenvalues, and all of them have to be non-negative, and that's if and only if this property holds. So that's roughly what you have here as well. But the punchline of that is that then, of course, we can talk about the square roots, right? And we can talk about the square roots very easily. So you see that's the square roots for the positive semi-definite matrices. So we can write for a positive definite square matrix B, a complex matrix, we can write its square root, and we can do it in such a way that first we notice that each such matrix is diagonalizable in some reasonable orthogonal coordinates. So we know that we find a matrix P such that P inverse times B times P, so conjugated B by P is a diagonal matrix. And the diagonals components are reals which are all non-negative. So we can take the square root of D simply as taking the square root of all the positive or non-negative real numbers on the diagonal, and then we simply go back by employing the same thing. And you see that if I multiply this guy with itself, then the P in the middle eats each other, so it cancels. The square root of D times square root of D, the two diagonal matrices will give you the original matrix with the eigenvalues of the matrix B, and then therefore Fu, so that will give you the D, and then of course you will get the right matrix B if you just conjugate back the coordinate change, right? So that's the positive definite square roots. And that's it. So that was a comment in the beginning, and now let's go on to the real task. So, and that's what to do in the situation where you have something like, say, derivative of polynomials, right? If you differentiate polynomials, so f would be, say, I don't know, ax squared plus bx plus c. So you have a vector f in R3, which is the same as R, well, rather, yeah, it doesn't matter. So R x of up to second order. And of course, if I map this to f dash, then I get 2ax plus b. And so you see that the matrix which I have to write, so this will be the matrix, and the matrix will be which? So I have to map the basis vectors. So if the basis vectors will start with x to 0, x to 1, x to 2, then this goes to 0. The first one, so that will be just x, that goes to 1, 0, 0, and x squared will go to 0, to 0. So if I, instead of my basis would take 1/2 of x squared instead, then I would get, instead the 2 here, I would get 1, right? So that's for another choice of the base. So the base would be, now for me the base is 1x and 1/2 of x squared, right? So that's the basis. And you see that the only eigenvalue of such a matrix, the only eigenvalue of this linear mapping will be 0. But if I look for eigenvectors, so the only eigenvector will be the first vector of the base, right? And there is no other linearly independent eigenvector there. So you see that the geometric multiplicity is strictly different from the algebraic multiplicity of the eigenvalue. And so we have to do something with that. And the reason why this happens is the occurrence of what we call nilpotent matrix, right? And that's here. So in general, we talk about spectrum of a linear mapping. So that was defined already before. That's the set of the eigenvalues, including multiplicity. So it's rather an n-tuple. So if it's nth order, well, it's n-dimensional space, so it will be an n-tuple of numbers, right? And it will be always, if a V was a complex vector space, then it would be an n-tuple of complex numbers. So spectrum is always well defined. It's the set of the roots of the characteristic polynomial, including the multiplicities. And I already told what the algebraic and geometric multiplicities are. Algebraic multiplicities, how many times we've got it in spectrum. Geometric multiplicity is the dimension of the relevant eigenspace. And a mapping F is called nilpotent if some iteration of it, so if I iterate it k times, give me identically 0. That's exactly what you see on the differentiation of the polynomials, and that's here. And we actually have an example of something which is called a cyclic mapping, because there is a basis of our space such that we have a chain of basis vectors, so that the first one in the chain is mapped to the second one, and the second one is mapped to the third one, and so on up to the case one if it's of order k, of degree k, the nilpotency, and then it goes to 0, right? And this is a very crucial thing, as we shall see. So this is the core of the concepts. So the nilpotency, the order of nilpotency, the algebraic and geometric multiplicities, and the special case of nilpotent things, nilpotent mappings or matrices, which are called cyclic. So, now you also see that the cyclic mapping, which we had here, so this one, was a special case of what we call here the Jordan block. A Jordan block is a matrix where you have the same lambda on the diagonal and ones over the diagonal. So here it was a Jordan block with 0 eigenvalue. Here it's general. And the crucial theorem I want to show you today is this one. And it's a theorem which is very easy to understand, right? It's very easy to understand. It's quite difficult to prove. And the theorem says that if I have got a linear automorphism on a complex vector space, but it works exactly as well in any field, over any field of scalar, if I've got enough eigenvalues, right? The difference, say, between real numbers and complex numbers is that over real numbers, if we deal with something like a rotation in a plane, then there simply will not be any real eigenvalues, right? So simply there are no eigenvalues there. But we can get them once we complexify. If we deal with something like this, there are simply no there is only limited number of eigenvectors, but there are the eigenvalues there, right? So, and the conclusion is that then each such vector space with respect to that particular mapping decomposes into a finite sum of, well, a direct sum of subspaces, so they are mutually disjoint, which are all invariant, and restriction to each of them has a single eigenvalue, and each of them is either a cyclic mapping, so its matrix would be a Jordan block, or it's a 0 mapping, right? So of course we also allow small blocks. So it's actually a Jordan block of size 1 by 1 is a 0 mapping, right? So 0 mapping consists of several such trivial Jordan blocks. Right, so either cyclic or 0, right? So in particular, it means that you always can find a basis of the vector space where the matrix of the mapping will become block diagonal. So it will be something like this, or no, something like this, and there will be blocks of different sizes, small one, a bigger one, and so on. And each of those blocks will be Jordan blocks. Jordan block. So either it's 0 or there is just the same eigenvalue lambda in one of those blocks plus the ones over the diagonal. And all the rest, everywhere else, you have got 0. Right? So it's block diagonal. And that's the claim of the theorem. So, as a corollary, of course, we see that it means that for each matrix we can find over complex scalar an invertible matrix P such that the conjugation of the matrix, such that A is obtained from a Jordan canonical form matrix, so the one with these Jordan blocks on the diagonal, via conjugation with P. P is then, of course, the transition matrix to another basis where you would get the canonical form. So the basis in which the canonical form is obtained is not unique. The shape of the matrix is unique up to the order of the blocks. So that's the complete result. Well, to have a little bit, say, more geometric understanding or view, you can also imagine that the theorem simply says, it's not clear that it's the same thing, but take it for being true. So if I have a mapping, say, phi, so I can write a phi as psi plus eta, where psi is diagonalizable, and eta is nilpotent. And on top of that, they commute with each other. Yeah, and you can imagine what it means in the individual Jordan blocks, right? In the individual Jordan blocks, you simply have if it's just one of those blocks, you have the lambdas here, that's the psi, and then you have the Jordan block with zeros here and ones here, that's the nilpotent part. Right, and you can check that those two commute, right? It doesn't matter whether I take first this one and then that one or the other way around. Right, so that's the more geometric description, and actually the description is pinned down uniquely by this requirement, and this is a description which is independent of the base, right, of the coordinates. Right, now how to come at least close to such a thing. So I think I will rather even not give much of the instructions here how to read a proof, because you simply have to digest it yourself. But I can add a few remarks, but before going into that, let's have a look what it means, right? Because now we, for example, can really complete our discussion of the behavior of Markov chains, because how would, if you start with some stochastic vector in a Markov chain of our type, this discrete one we discussed some time back, then once you have your stochastic primitive matrix, which runs the iterative procedure, then of course you can find the Jordan canonical form for that, right? Or you can find this nice decomposition, and then you find simply a decomposition to spaces where the eigenvalue will be the same, and for each of those cyclic ones, because you see that the nilpotent part here simply splits into, so this one splits into a sum of cyclic maps, right? So that's how it looks in the individual Jordan blocks. And then it means that simply what we were explaining, how the eigen subspaces which were corresponding to the eigenvalues with absolute value less than 1, how they disappear because the absolute value is smaller than 1, and by iterating the matrix they simply start disappearing. So here, instead of disappearing, they will be something like jumping along the chain in the nilpotent thing. So if you subtract lambda times the value, then the rest which leaves is the cyclic map, and so you will jump. So it will simply, roughly speaking, asymptotically, it will disappear at the same speed, except it would always need as many jumps through the chain as the degree of the nilpotency in the block, right? So we are again at the same result, that everything dies out, and that's due to this understanding of the general character even of those bodies where you don't have enough eigenvectors. Right, so that's how to understand the result and why it's reasonable, and here you see it more explicitly in the text. That's exactly what I was now trying to indicate. And I also touched already what we call the root spaces, right? So where we get is, instead of wanting that the mapping would have values which are A times some unknown A times identity on some subspaces, which is the definition of the eigensubspaces. We simply want that this happens in some power. We don't care which power, but in some power. And this is called a root vector and root space for the given linear mapping phi. And now the crucial but not that easy theorem is saying that where do I have it? Not here. Here. This is one of the crucial steps on the way. You simply have a linear mapping, you find all the distinct eigenvalues, you write down the root spaces for them, and it's possible to prove that actually the whole space is a direct sum of these invariant subspaces. So actually for each linear mapping I've got a decomposition of the whole space into root spaces. This is the first step. On the way to come here I need what I was already going through before, so it's some properties of the root spaces, but in particular, and that's worth a special stop, it's the concept of the quotient spaces. That's again something which you could meet very easily and very often in handling data. Simply by introducing some simplification, you can be more fast and more precise in categorizing and deciding things, and that's usually in common sense thinking expressed in a way that we compare things up to some, say, properties which are not of interest now, so neglecting something which is smaller than, or having colors which are not interesting, or I don't know what, right? And with linear maps and vector spaces, this is made very explicit and nice. So if you have a vector subspace, we can say that two vectors are the same up to something in the subspace, simply saying that that's the same as saying that their difference sits in U, right? So I come from one to the other by adding simply an element from the fixed subspace. So for example, in real plane, well, again, so that's the real plane, and in the plane I decide that I would have a subspace like this, so this will be my U. And then, of course, if I want to see whether two vectors are different only up to something in U, it means I split the whole plane into parallel lines, right? Because having two vectors, so if this is the U, so I have the origin somewhere on U, so there's a subspace. So you see the two vectors have got difference sitting in U only if they sit on a parallel line to U. So I simply decompose the plane into parallel lines to a given subspace U, and this is the same thing as telling that I'm interested in some properties, but I measure them only up to the changes in U. And this is general for all vector spaces and subspaces, and it's called a quotient space. And now, clearly, if I have such a subspace, then I can pick up a basis of such a subspace. And of course, if I complete this basis into a complete basis, then there will be n minus k additional vectors in the basis left, and I can consider them as representatives of the classes in the quotient space, which we just understood what it is. and this will be a basis of the quotient space. And using this concept, we can induce mappings on quotient spaces. So if our subspace U was an invariant subspace, then it means that in the completed basis, starting by some basis of this subspace and completing it to a full space, the matrix of the mapping must be this. And of course what happens is then that the mapping automatically generates the induced mapping on the quotient space, because U is invariant, so it makes sense. And in the induced basis, which we just introduced on the quotient space, the mapping will have matrix D. So that's here. Right? And this can then be used if you on top of that add the scalar product to the vector space, so we can have an orthogonal triangulation result, which I mentioned already. That's the very useful Schur's orthogonal triangulation theorem. And this one says that if you start with any linear mapping on a vector space with scalar products, so either real or unitary, then you always can find an orthonormal basis such that the matrix will be upper triangular and the eigenvalues will be on the diagonal. So there will be the eigenvalues there, and it will be upper triangular. That's quite straightforward and easy, so you are invited to browse through if you like it. So this is independent and very useful and very crucial for general understanding, but here it was just put inside of the flow of the text because it was strictly necessary to know all this to prove this theorem I was already telling you, right? So you see here I have one of my favorite pictures. There's one. Right, but this is not the end of the misery, because once we know this thing about the root spaces, we already know a part of what I try to indicate here as a more geometric picture, because we already know that there will be some decomposition like this, but we are still far from knowing that this will be giving you the normal, the Jordan blocks, right? So and also so that's linked to the fact that there would be psi, which is diagonalizable, there would be eta, which is nilpotent, but we wouldn't know this, and we wouldn't fix the Jordan blocks the nice way. And what's still missing is the fact that for the nilpotent eta with the same eigenvalues, well, so we restrict to one root space. We subtract the eigenvalue times identity, and what we are left with would be a nilpotent mapping, right? And now we want to conclude this by saying that whenever we have got a nilpotent mapping, it always decomposes into direct sum of subspaces on which the mapping already acts in this nice cycle, so it's not only nilpotent but cyclic. And this is quite an annoying technical proof, which is constructive but not that easy. And still then there is a little bit to conclude, but it's already, once you would digest the previous one, you would survive this. So this is about the Jordan canonical form, Jordan canonical matrix, etc. Here is a try to describe a sort of algorithm. There are also some special tasks with solutions, so you can go through, and it's actually done explicitly for this kind. So I think it's more than enough. I should perhaps have split this explanation and presentation into two. It's already nearly half an hour, so it's highest time to stop here. Have a nice day.